So let's discuss the contraction mapping theorem of Banach, which also happens to be Banach's PhD thesis, apparently. So we start with this series of interconnected definitions of various kinds of self-maps. By self-maps, we mean mappings from a set to itself. So definition 17 says, let S rho be a metric space and let T be a mapping from S into itself. And then T is non-expansive if the distance between Tx and Ty is less than or equal to the distance between x and y for every pair of points x and y in S. Right? And T is a strict contraction if the distance is strictly less whenever x and y are two distinct points. T is a uniformly strict contraction with modulus lambda if the distance between Tx and Ty is less than or equal to lambda times x and y, where lambda is less than 1, right? So to fix ideas, let's take an example here. So let S be the closed interval from 0 to 1, right? And let T be defined by Tx or T of x. So we normally use the notation Tx rather than T of x, right? So let Tx be linear affine and let's just draw this here, right? So we have a -45-degree line, the reason for which will become more apparent as we travel a little bit further. So let's draw some maps. So this is the graph of a T which is defined by Tx is equal to x. Okay, and let's draw another. So this is a different map. We can call it T again. So let's say that is, 1/3 plus whatever, 1/4 times x, right? So if you look at the red map, it has the property that if I were to take a pair of points x and y, that's the distance between x and y. And then I have tx and ty, tx and ty, but tx is equal to x, ty is equal to y, so the distance between tx and ty is exactly equal to the distance between x and y, right? So this trivially satisfies the notion of T being a non-expansive map in the sense that the distance is less than or equal to x and y, right? Now, if you look at the map drawn in blue, so here, this is that's my tx, and if I want to see tx, because domain and codomain are the same, if I want to see tx here, I take x, I go up to tx, and I reflect it off the 45-degree line, so that's tx. Ty, so I go up to the t function here, and that's my ty. So off the 45-degree line, it's somewhere here, right? So because the slope here is a lot less than the slope of the 45-degree line, the distance between tx and ty is getting squeezed, right? So in this particular blue example, the distance between tx and ty is less than the distance between x and y, right? And we can say something more. So the blue example is a special case of a tx defined by a plus bx, where in absolute value b is less than 1. So if that's the case, then what's happening here? So we have rho tx ty. In this example is just the absolute distance between tx and ty. So that's a plus bx minus a minus by. So that's absolute b times x minus y, and that it just acts as a norm, so it must satisfy this property of a norm, which we know that it does, right? So the absolute distance between tx and ty is equal to norm b, or absolute value of b, times absolute distance between x and y. So you can see that in particular this is less than the distance between x and y, right? But notice also that so what we have here in this example is a strict contraction whenever the absolute value of b is strictly less than 1, right? But we also have that this satisfies that rho tx ty is less than or equal to absolute value b times rho xy, yeah? So because it's equal to, we can put it this way, and so we can say that T is a uniform contraction with modulus absolute value of b. Okay, so notice that when you have this kind of contraction where the absolute value of b is less than 1, and you take any pair of points x and y, then the distance between tx and ty gets squeezed between this distance. Okay, so the distance tx ty is less than or equal to the distance xy. Note that if t is non-expansive, then t is also a continuous function or a continuous map, right? So what is being said is, suppose t is non-expansive, then that implies t is continuous, right? So suppose xn is a sequence in the domain converging to x. We want to show txn is a sequence in the codomain, which again is the domain itself, that converges to tx, right? Provided t is non-expansive. So what's happening here? Well, non-expansiveness has to do with distances between tx's and ty's, right, for a pair of points x and y. So let's bring in distances here. So suppose my pair of points is some xn and some x. Okay, so non-expansiveness would mean that the distance between txn and tx is less than or equal to the distance between xn and x, right? So now we've a sequence xn that converges to x, so that means that the distance between xn and x goes to 0, right? And therefore this distance, which is always less than or equal to this, gets squeezed and goes to 0 as well. Okay, so txn converges to tx, right? So t is continuous. And a second thing to note is that if t is a strict contraction, then it has at most one fixed point. Okay, so what is being said is, t strict contraction. So what does that mean? So take x and y that are distinct, and a strict contraction says that the distance between tx and ty is strictly less than the distance between x and y, right? So what's being said is that in that case, there is at most one fixed point, right? And so you can go through this little proof. The point is very simple. Suppose x and y are fixed points, right? So by definition, a fixed point of a mapping is a point that the mapping carries to itself, right? So fixed point means that if I apply the mapping tx, that's going to not change my position. So tx is equal to x, and similarly ty is equal to y, right? But then, so tx and x are the same point, ty and y are the same point if x and y are fixed points, right? But then if I look at the distance between tx and ty, I'm saying, look, this is exactly the point x, and this is exactly the point y, right? So then the distance between tx and x must be exactly equal to the distance between x and y, right? So now if x and y are distinct points, then this contradicts that T is a strict contraction. Okay, for a strict contraction, we should have that the distance between Tx and Ty is strictly less than between x and y, right? So we'd already done this linear affine example. Example 2 here is one where the mapping called F here, let's just call it T. The mapping T is a strict contraction but not a uniformly strict contraction. And this is an example to show that if you simply have a strict contraction, a fixed point may not exist. Okay, so consider this mapping T from 1 to infinity to 1 to infinity, defined by Tx is equal to x plus 1 by x. Okay, and so what is the distance between Tx and Ty? So that's x plus 1 by x minus y minus 1 by y. So I can rewrite that as x minus y times 1 by x minus 1 by y. So that's x minus y times y minus x by xy. So that's x minus y times, right? So now notice that x is greater than or equal to y. Sorry, x is greater than or equal to 1, y is greater than or equal to 1, because my mapping is from 1 to infinity to 1 to infinity, right? And I have two distinct points, x and y. So if I have two distinct points, then xy is strictly greater than 1, if x is not equal to y. Right, and so 1 minus 1 by xy is strictly less than 1. Okay, so T is a uniformly strict contraction. But as you can verify, Tx is equal to, so there does not exist x such that Tx is equal to x, right? So Tx we know is x plus 1 by x. So there is no x such that x plus 1 by x is equal to x, right? So no fixed point. And by way of an aside, if I want to show what the graph of Tx here looks like, so again take the 45-degree line. Yeah, but I want to take Tx from 1 to infinity, right? Yeah, nevertheless, let me just try and plot this function tx is equal to x plus 1 by x. So if I look at positive x's, I have that 1 by x is positive and 1 by x goes to 0 as x tends to infinity, right? Tx is equal to x, that's just the 45-degree line, right? So x plus 1 by x, because 1 by x is positive, must lie above the 45-degree line here, okay? And it goes, the 1 by x part goes to 0, right? So it must be that, this is some curve that's going to the 45-degree line. It has an oblique asymptote, goes to the 45-degree line from above, right? And as x goes to 0, this goes to 0 and 1 by x goes to infinity. So it must be looking like that, right? So this is it's a quick and dirty way rendition. And you can see that there's no fixed point, right? And if you want to draw the entire graph, then you just note that t is an odd function, so there must be something symmetric here. Right. So we come to the main theorem, which is Banach's contraction mapping theorem, which says, suppose S rho is a complete metric space, and suppose T from S to S is a uniform contraction with modulus lambda less than 1, then T has exactly one fixed point. And here is the idea of the proof. So you have so that's my T, or that's my graph of T. And so here's what the proof does. The proof starts at any point x naught in the domain. So suppose we start here. That's our x naught, okay? And then it considers a sequence xn defined by each xn is t to the n x naught, that is an n-fold map of t, okay, where tn operates with the map t n successive times on x naught, okay? So what does the sequence look like? So that's, if I operate once, so that's my tx naught. And what does the point tx naught look like in the domain? It's this point, right? So that's operating once, okay? And then suppose I operate once more. So this point is t of tx naught, okay? And what does that look like? In the domain, it's this t2 x naught. And then I operate once more. So I get and then I carry that point back to the domain. That's t3 x naught, and so forth, okay? So these points are being called xn, where for each n, xn is tn x naught. I've operated on x naught n times. So I've hopped n times from x naught, okay? Hop once, hop twice, etc., etc. And you can see that my hops are becoming weaker and weaker. So it's reasonable to guess that these things are clumping towards some limit in a Cauchy kind of way. And the assumption that the metric space is complete will mean that this Cauchy sequence will have a limit in this metric space, right? So going step by step, the first step is I want to show that this sequence is indeed Cauchy, okay? So suppose I assess the distance between xn and xm, okay? xn, n hops from x naught, xm, m hops, okay? And suppose m is greater than n, or greater than or equal to n, okay? So this is a uniform contraction with modulus lambda. So what's happening is that the distance between these pair of points is less than or equal to the distance between so how do I get n hops? So I start with x naught, I hop to tx naught, I hop to tx1, keep hopping, and I arrive at txn minus 1, and one more hop brings me to txn, right? So it must be that rho xn xm is less than, so that's the same thing as rho txn minus 1 txm minus 1, okay? Right, so I arrive at xn by one additional hop from xn minus 1, okay? So I guess this is, yeah, right. So this must be less than or equal to lambda times the distance between xn minus 1, xm minus 1, okay? So once again, the xn is obtained by n hops from x naught, okay? So I go to tx naught, that's something that I'm calling x1, right? I hop once from there, so that's a tx1, which is my x2, and so forth. And then I arrive at this is my xn, and this is something which I can ignore, right? So there was an xn minus 1 here, and with an additional t jump, I arrive at xn, okay? I had defined these in terms of just carrying x naught through multiple hops. So this was tx naught, this was 2 hops from x naught, so t2 x naught, then 3 hops from x naught, and so forth, until I come to n hops from x naught. Yeah, so what's being said is n hops from x naught is 1 hop from xn minus 1, okay? So xn is 1 hop from xn minus 1, and xm is 1 hop from xm minus 1, right? So the distance between xn and xm is exactly the distance between t xn minus 1, t xm minus 1, and that's less than or equal to lambda times the distance between xn minus 1 and xm minus 1, okay? So that's this inequality. And I can do the same for xn minus 1 and xm minus 1. So this is less than or equal to, I take the lambda out, this is less than or equal to lambda times the distance between xn minus 2, xm minus 2, right? So that's lambda squared distance xn minus 2, xm minus 2, right? And I do this n times, and I come to the conclusion that the distance between xn and xm is less than or equal to lambda to the n distance between x naught and xm minus 1, xm minus n, okay? So I've squeezed this distance between x naught and xm minus n times to come here, okay? And then note that this distance between x naught and xm minus n, right, it's using the triangle inequality, it's less than or equal to the sum of distances between x naught and x1, x1 and x2, x2 and x3, all the way to here, okay? And finally, note that, so x1 to x2, x2 to x3, and so forth, yeah? And finally, note that the distance between x1 and x2 is less than or equal to lambda times the distance between x naught and x1. Similarly, this is less than or equal to lambda squared times the distance between x naught and x1, and so forth, okay? So what is being said is, if I start with this distance and then I hop, I come to, one hop from x naught, one hop from x1. So this is less than or equal to, and then I hop again, one hop from x1 is x2, one hop from x2 is x3. So that's less than or equal to lambda times rho x1, x2. That's less than or so that's less than or equal to lambda squared times distance between x naught and x1, right? So I go from here to here, and that's less than or equal to distance between x naught and x1 times 1 plus lambda squared all the way through this. And that's just a geometric series, so it's less than or equal to the infinite geometric series, which sums to 1 by 1 minus lambda, distance between x naught and x1, right? So we've established that in the sequence xn, the distance between 2 points xn and xm is less than or equal to lambda to the n times 1 by 1 minus lambda, distance between x naught and x1, okay? So this is my x naught, that was my x1, that was my x2, that was my x3, and so forth, okay? So the right-hand side here can be made arbitrarily close to 0, which means that the distance between xn and xm can be made arbitrarily close to 0. So it must be that xn is Cauchy, right? So if you want, you can define Cauchy rigorously and show that indeed by this argument xn is Cauchy. And because it's Cauchy and S is complete, xn converges to a limit x in the set S, right? So now it is claimed that this limit x is a fixed point of t. So why is that? Well, xn is Cauchy. it converges to some limit x, right? T is uniformly strict contraction. So that means it's obviously non-expansive. It's more than non-expansive. That means it's continuous. So that means Txn converges to Tx. But note that Txn is really the sequence xn in some sense, right? So what is xn for every n? It's just n applications of t to x naught, right? What is Txn? It's just t times Tn x naught. It lies on the same sequence as xn. It's the next point, right? It's my xn plus 1. So a sequence converges to a unique limit. So xn and Txn are essentially the same sequences. So these two limits must be the same, okay? So x must be equal to Tx, that is x is a fixed point of t, right? Moreover, this T is a uniformly strict contraction. So in particular, it's a strict contraction, and we've shown that for strict contractions, they have at most a single fixed point, right? And so this is the unique fixed point of T.